Hey guys, this video is about determining the rate law from experimental data. Consider the following reaction. Nitrogen dioxide can react with carbon monoxide to produce nitric oxide and carbon dioxide. This is a reaction that takes place in your cars, in the exhaust area of your cars. And this is the rate law written with variables. We can write the rate law the rate is equal to a constant times NO2 raised to the m power, this is a variable, and CO raised to the n power. We just use the reactants when writing the rate law. In order to determine what K is, what m is, and what n is, we need to use experimental data. And the scientist here did 3 experiments to answer that question. And each of these rows represents a different experiment. What you should notice is that, let's compare 1 and 2. When we have the initial concentration of 0.1 molar of each of NO2 and CO, we have a reaction rate that is measured to be 0.0050. The second reaction that the scientist ran, they left the CO concentration the same and only changed the NO2. Notice that when he did that, or she did that, the rate went up. This allows us to look just at the NO2 because the CO remained constant. So this was a conscious choice. The scientists wanted to figure out how the rate would change with regards to changing the NO2 so that he or she could figure out what that M value is, what the power or the rate order of the nitrogen dioxide in the reaction is. So when we do this, we compare these two rates. I put the larger rate on top and the smaller rate on bottom. I am going to compare rate 2 to rate 1 here. And the rate expression for rate 2 is the NO2, where I'm using this expression here when I'm writing this. And it's K times the NO2 raised to the m power times the CO raised to the n power over K times NO2 raised to the m power and CO raised to the n power. Now, several of these things just cancel right out because they're the same. K divided by K is going to be 1. If I don't change the reaction temperature, the K remains the same for both of these reactions. Moving on, because the carbon monoxide values were both 0.1, we can also eliminate this, which leaves us to plug in only the NO2. And, when you divide by these powers like this, we can take both of them out and raise them both to the power of m. That's a mathematical principle. So if I take the NO2 in the second situation, 0.40, and then I have it in the first situation, 0.10, I get 0.1 divided by, or 0.4 divided by 0.1 is 4.0 raised to the m power. I still haven't solved for m yet, but here's where these numbers come into play. I then divide 4.0 times, or to the raised to the m power is equal to the rate 2 over rate 1. 0.080 over 0.0050. These two numbers simplify. Back up there. These two numbers, 0.08 divided by 0.005, and your calculator simplify to 16. So 4 raised to what power is 16? 4 squared is 16. So m is equal to 2. We figured out now what the reaction order for the NO2 is, right? We figured out that m is equal to 2. Now we need to figure out what the n value is. So this time, instead of looking at the reaction where CO was held constant, we're going to look at reactions 1 and 3. Notice here, NO2 is held constant, but the CO is actually what has changed. So if we write the rate law, that not this time of 2 over 1, but 3 over 1. The rate of 3 over the rate of reaction 1, that's equal to, we can ignore the NO2s. We can just look at the CO raised to whatever power. K's cancel, and the CO in reaction 2 is 0.20. The CO in reaction 1 is 0.10, and they're raised to the n power. 0.2 divided by 0.1 is 2 raised to the n power, and that's equal to, hey, hold on a second. The rate 3 is 0.0050, and the rate 1 is 0.0050 also. That simplifies to 1. So 2 raised to the what power gives you 1? And it has to be 0, because any number raised to a 0 power is 1. So what that tells us is the rate is actually independent of the carbon monoxide concentration. We can then write the rate law. Rate is equal to K times NO2 squared times CO to the 0 power. We could even actually rewrite this without the CO altogether, because the CO does not factor into the rate of this reaction. Ultimately, what we're going to learn later on in the unit is how this plays into the reaction mechanism. It tells us that ultimately that CO comes in after the slow step of the reaction, but we'll get to that later. One more thing you might be asked to do on the AP exam is figure out what this value K is, because we really still don't know what that is. The easiest way to do it is to do what we've just done, to figure out the rate law, because the rate law is written usually with the K in it like that, but then we take a look back at some of the previous reactions. I'm just going to take reaction 3 here. Now we have all the data that we need to figure out what K is. So for reaction 3, or reaction 3, the rate there was 0.050, and let's look at those units, because it becomes really important here. Moles per liter times seconds. So moles per liter times seconds. So it's moles per liter per second. Mole per liter per second. And that's equal to our unknown K times, back in this scenario here, NO had a concentration of 0.10, and now we know that it's raised to the second power. We don't have to put in the information for the CO because raised to the 0 power, it's just a 1. The one thing I did neglect to do at the end, a little bit of a boo-boo here, is I really do need to write in the units. K is a very tricky thing. K, the units change depending on the rate order, so you have to rederive the units every time. And the units for these are concentration units, right? Moles per liter. So I've put those in, and now I'm just going to solve for K. K is equal to 0.0050 moles divided by liters times seconds divided by 0.1 times 0.1 is 0.01. And now I do have to also square the moles and the liters. When I do this, I get 0.50 when I divide just the coefficients here, just the values. And let's look at these units. If it's moles per liter times seconds, and I divide this by this, I invert the bottom and multiply. So liters squared times, whoops, not times anything, liters squared divided by moles squared. This, of course, reduces to moles to the 1 on the bottom and liters to the 1 on top. So my final value for K is equal to 0.50 liters per mole times seconds. I could also rewrite this if I wanted to in a different way. Liters over moles is molarity upside down. So my units could have been molar to the minus 1, seconds to the minus 1. Because the seconds is down in the bottom underneath that, underneath the division sign. So some problems don't expect you to solve for K, but if they do, this is how you do it. Alright, that's it for now.